All right, I thought I'd take you through a little graphical exercise. Um, just initial conversations here. We're never gonna get good at something until we start talking about it and start working with it. So let's have a little go here. This is the first year that I have not taught the unit circle prior to teaching how to graph a sinusoid. Kind of reverse the order, but I think it's working out fine. We've talked about moving around the center, moving around a circle, the circumference being 360 degrees. And we started talking about what a radian measurement is, and I think we have to talk about that a long time before you start to grasp it. But I tried to make a circle where the marker was 1 unit long, and then I made the x-axis the cutting the circumference, opening it up. So the x-axis is the circumference of the circle, and I didn't batch it up greatly because of a crack in the wall over here. But I said 1 radian, 2 radians, 3, and I marked some x's here, like there's one right after 3. Maybe you're already trying to sort out that I'm looking at 3.14, and you'd be right. And at the end, 6.28, which is really circumference of the circle when the radius is 1, 2 pi r, radius of 1, 2 times 3.14. About 6.28 of these lengths is what it would take me to walk around the circle. And as I walk around the circle, if we draw triangles, the height is actually the sine function. It's opposite the reference angle at the origin, because we're going to put an xy axis in here. And so that altitude is the sine function. And so the biggest it ever gets is straight up, where the radius matches with straight up and height of 1. And that takes place at 1.57 radius lengths. There's one radius length and another 0.57. And if you saw that as pi over 2, good for you. All right, that's an exact value. This is an approximation. And I think, if I remember correctly, 3 pi over 2, which is 90, 180, 270, I get my minimum height of -1. And I think it's 3 times, what's 3.13 times, 3 times this is what I'm talking about, right? 3 times pi over 2, 3 pi over 2, 270 degrees, 1.57. I believe it's 4.71. Check that if I'm wrong. We'll correct it. And so what's the range of the sine function? That was on your last test, the range. All of my heights are either less than or equal to 1 or greater than or equal to -1. So the sine function is got a multiplier in front of it. It's a 1. And it's got a midline, 0, because I'm going up 1 and down 1 from the middle, which is 0 in this case. That's the number between 1 and -1. And we don't write these. But we probably have to remember that they're there, because what happens when I make this 5 and I change this to be x minus 2 over 3 and I make that a 7? How does this graph change? Well, I used to have things that were coming out of this 1, -1, but I'm multiplying by 5. I think this is going up and down by 5 now. I think we have amplified our peaks and our valleys. And I don't think I'm at 0 anymore. I think I'm at 7. So that's not 1. If I measure from 7 and I go up 5, that's now 12. And if I go down 5 from 7, that's now 2. So my range in this function is no longer 1 to -1. It sure looks like it's 12 to 2, which is 10 units, which is the diameter of my new circular situation. All right, so let's have you try one of those. See if you can graph. Remember, we're just starting the conversation. Don't expect to pick this up immediately. Let's look at y equals, how about we do 4 times the sine of x over 8 plus, let's do 11. All right, so you pause the video and you have a go, and I'll just show you what I think it looks like. So I'm going to get my frame of reference here. I'm going to get my range. Midline is 11, going up 4 and down 4, 15 to 7. So my range is less than or equal to 15, greater than or equal to 7. I hope you can spot that right from the get-go. Hope you can spot the midline and the amplification. And I know that if I pick the right numbers, like the sine of 0 and the sine of 2 pi, Think I'm gold? Well, what makes x over 8 equal 0? Hope you say 0. So 0 gets me the midline value, 11. And what makes x over 8 equal 2 pi? Hope you're saying 16 pi. Brings me back to 11, which implies that this should be 8 pi, getting me 11, and this should be 4 pi, getting me 15. Let's do that one. We've worked with this situation quite a bit, right? In the sine function, that's pi over 2. In the parent function, pi over 2. All right, so let's put 4 pi in. Oh, 4 pi divided by 8 is pi over 2. Oh, and what is the sine value? Well, that's an x, that's a 1. 1 times 4 is 4, plus 11, 15. And we're starting to fill in some tabular values to help us visualize all the solutions to the equation for sine pi x over 8 plus 11 y values. We could get more. We could find this one easily enough. And with more practice and trig, we can find when it's halfway up, when it's 0.87 units above as a multiplier. And we'll be practicing that after midterm. But right now, we're getting the conversation started. And this is following a pattern of either making zeros or using zeros or making ones and using ones. Math, multiplication, addition, and subtraction are a whole lot easier when you're working with zeros and ones. All right, so I'm going to do the same thing with this function. All right, so I'm looking at f of x equals 3 to the x. I'm looking at the trends. I'm picking x values like -3, 3 to the -3, 1 over 27. We've practiced that. This stage of the term, that should not be hard to see. 3 to the -2, 1/9. 3 to the -1, 1/3. What are my y values doing? They sure look like they're increasing. What are my x values doing? They sure look like they're increasing. My x values appear to be changing by 1, just like counting numbers. These changes, that looks like a pretty small change in y. That looks like a much bigger one. So I put letters A, B, C, D, E, F, and G, and I use those letters to look at kind of the pattern. A, B, not changing much. 1/27, 1/9, 1/3. I'm trying to change by 1 each time. Change by 1 each time, but my changes are getting bigger. That's a jump of 2 from D to E. That's a jump of 2. From E to F, that's a jump of 6. That's going to be twice that jump. And then the next one is going to be 3 times that jump, 18. All right, and I'm hoping we can see the general trend of exponential growth and the asymptotic behavior here. Where's the asymptotic behavior? Well, as I go from 0 to -1 to -2 to -3 to negative infinity, it sure looks like 1/3, 1/9, 1/27 is heading to 0. Oh yeah, we don't write the 0. But that's the asymptote. That's a multiplier. So let's, like we did with the last function, give you a new one. And I like using a D and E. D and E, because 0 and 1 give me a 3-to-1 ratio. And so that means I can pick a differential, make it 3 times bigger every single time in this case. So I want 3 to the 0, which gets me a 1. And I want 3 to the 1, which gets me a 3. It's easy to do, provided I pick the right numbers. All right, so you pause the video and fill in the blanks. Y equals, how about we go 12 times 3 to the x minus 2 over 5 plus 7. All right, you pause the video and have a go. I'll just keep talking. Well, I know my midline is 7. I know my first jump is 12, and I know my next jump is going to be 36 if I make this happen. 7 and 12 is 19. 7 and 36 is 43. And how do I make the argument of the function? 0. You've been doing that with the equation of a line since day 1. Pick a 2. Let's put it in. 2 minus 2, 0, 3 to the 0, 1 times 12, 12 plus 7, 19. How do I make x minus 2 over 5 equal 1? Well, I'm changing the number 2 by 5. Now, I'm sorry, I got the same number in there. I don't like the same number anywhere. All right, so I'm going to change this one to 6. That means this is now a 6, which means this has gone down 1 to 18. I still got 8. Well, let's see. Let's go back to what it was. 7, 19. All right, just have to deal with it. All right, so this is then 7. I just don't like those two 7s. This is the midline. That's that 7. All right, we'll do one more here. And we won't show the differentials, but let's see if you can speed up your work by graphing the following. Y equals, I'm not going to use those now. I'm going to use 8. I'll double. Let's double 4x minus, how about 20 plus 11? There. I don't think we'll see any funky numbers show up here. All right, you pause the video and see what you can do. I'll look at it and graph it. I see midline of 11. My first jump is 8, so that takes me to 19. And my second jump is going to be 16 plus 11, 27. And it's going to be twice this distance. Twice that distance looks to be about there for me. And so that, what did I say it was? 16, 11, 27. What makes the number 0 here? I'm seeing 5. What makes the number 1 up here? 21/4. Not the friendliest number. Okay, but sure looks right to me. And so when I put in 5, 2 to the 0, 1, 8 plus 11, 19. When I put in 21/4, what happens to the 4s? Cancel. I get 2 to the 1. I get a jump of 16. Now, I hope you can see the 8, and I hope you can see 16 because I'm doubling the first jump. The next jump would be 32. So, but that doesn't seem like it's the friendliest number. 52, 13, not bad. It's not bad. So when does this thing equal 2? 4x minus 20. But I lost my train of thought. I totally lost my train of thought. Yes, 2 to the 2. That's what I want. So 22. Okay, so it's not the friendliest number, but you can work with it. I thought I had 52 there for a second. Okay, so let's do the inverse of this. Let's graph the inverse. So you go ahead and pause the video and graph the inverse. I'll just keep talking. Well, what do you do when you do an inverse? You switch the x's and the y's. Y equals 11 becomes what? I hope you say x equals 11. And I hope from your pre-algebra days you graphed x equals 11. There it is. What used to be a horizontal asymptote is actually vertical now. And what's the inverse of 519? 19.5. I know you can't see that, but that was what we had over there, 519. So let's go 19.5. And just for the record, how far is it from 11 to 19? 8 units. I think we saw that over there, didn't we? Didn't we see a vertical differential of 8? Well, now it's a horizontal differential of 8. And if we're doubling over there, our next one's going to be twice that. That's going to be a differential of 16. 11 plus 16, 27. I do believe that's what we had. Yes, that's what we had over there. And we used 21/4. And there's that graph. That's the inverse. The inverse of going up fast, exponentially going up fast, going up slow. The inverse of leveling off is vertical down. Inverse of horizontal, vertical. And that's what we're beginning to get here. I'm not sure that language fits exactly, but it was my first attempt at trying to say that in that way. Okay, so how would I write this function? It'd be nice to be able to go from graphs. All right, well, the inverse of that, these are y values. I don't see a most important y value here. I see a first from left to right, and I see 5. I think I'll go there. How do I get to 21/4, which is 0.25? I think I go up 0.25. All right, I'll work with that. And it's a logarithm. Don't usually use this. Maybe I should use 1/4 since it's a math class. 1/4 the log. Well, now I'm dealing with the x's. Okay, well, over here, these numbers really got small. In fact, they approach 0. Yeah, in fact, I can't get a 0 out though. I keep getting like 1/81, 1/343. Well, looks to me like we're approaching 11 on this one. So I'm guess I've got to write x minus 11. And the reader needs to know that log 0 is undefined. But log of 1/343 isn't. So I need positive numbers. All right, and so what's going to be a positive number for x? Numbers bigger than 11. How much bigger is 19? 8. 19 minus 11 is 8. So when I put 19 in here, I get log 8/8. I don't even have a base, but I know what that is. Doesn't matter what the base is. That's a 1. And what exponent do you put on top of a base to get a 1? A 0. And 0 times 1/4 is 0 plus 5. I just got this number. Now I want to get 21/4. Well, I got another number I can use, 27. And what's 27 minus 11? 16 divided by 8. Let's make that base 2. So when I put 27 in, I get log base 2 of 2, which is 1 times 1/4. 1/4 plus 5, 5 1/4. And it wasn't even the friendliest number, but you can get them quickly and easily. All right. So one last one. Let's just do the cosine function. Let's see what it looks like. The cosine function measures width in the unit circle. And if I start my walk here, then I haven't moved. And what's the width? Well, that's the radius. That's 1. So the cosine function starts at 1, acts just like the sine function, goes from 1 to -1, back to 1 in this case. And so that's one period of the cosine function if I'm starting with my argument being 0. And when will it finish? 2 pi. That's 1 revolution. So how does this change? How does this midline of 0, 1, -1 change? Well, my midline now is 20. My amplitude is 4, so I go up to 24. I go down to what, 16? What makes a 0? 0, but now it gets me 24. Why? Because the cosine of 0 is 1, and 1 times 4 is 4, plus 20 is 24. And when will this equal 2 pi? When I simply let x equal pi. That's the end of the revolution. Go Che. Again, I don't know what kind of fellow Che was, but I know he's a revolutionary, and we're at the end of the revolution. That's the guy with the beret that they put on the t-shirts. It's a generational thing here. I guess you had to be in the 60s to get that one. All right. So pi gets us 1, and now pi gets us 2 pi. And what is the cosine of 2 pi? The width over here after I go around once. And that's still 1. It's a unit circle. That brings us back to 24, which means that pi should get me 16. And the one we're familiar with, well, we're not really familiar with the cosine function as much as the sine at this point. So we can stop there. So what's the period of this function? 0 to pi. That's roughly 3.14 units on the x-axis, right? Now, why is that half of what it was before? Because if you double what you plug in here, you only need half as much to get the job done. If you're working twice as hard as you did yesterday to do a job, it should take you half the time. So if the normal function, cosine x looked like this, I'll get a start and a finish, top to bottom to top. Then the new one times 2 is top to bottom times top. It happens faster. I don't know. Probably could have done a better job of drawing that. All right, so I just wanted to get this conversation started. Got to process things, and brain can't process things till you hear them and look at them. We've started. All right, we've been doing that for a while, but maybe that clarifies things a little bit. And we'll continue to find different ways to talk about it and play with it and get a little stronger foundation. So that if I ask you to find the area bounded by the sine and cosine curve from 0 to pi, I don't think I'd do that, 0 to pi over 2, you might be able to draw it. And then when you get to a calculus class, you can study the calculus and not have to worry about drawing it. Because when you come out of this class by May 15th, I'm hoping everybody can draw these things quickly and easily. That's our goal. All right. Stay safe and warm.